Alright, today we are going to go over briefly the large formula map of everything Gen Chem. Everything Gen Chem 1, Gen Chem 2 for the MCAT. There's a lot going on here, so we're going to take it step by step, kind of similar to how we did the equations for physics. And if there's anything really complicated that needs a deeper dive, I can make a separate video on that. But for now, let's just jump right in, starting with stoichiometry. Avogadro's number, good to know, 6.02 times 10 to the 23. If you've taken lots of chemistry classes, you probably know this number by heart. Sometimes they'll give it to you, sometimes they won't. Molecular weight is grams per mole. If we move that equation around, we get number of moles is the mass over the molecular weight. Classic chemistry right here. Present composition by mass. Mass of X over total mass times 100. Pretty self-explanatory. Mole fraction, moles of S over the total moles. Again, kind of self-explanatory. Molarity is moles over volume, so moles over liter. And molality is not on here, but that is moles over kilograms. Sometimes I'll ask about that. Nuclear and atomic chemistry. So this is where we get into our different types of decays, electron energy, all that good stuff. So the energy of a photon is going to be HF, or hc over wavelength. We also talked about this. It's in our physics equation sheet, but this is also used for chemistry. Electron energy, this one's not as important to remember. Just memorize that N is the energy level and that the relationship between the energy level is going to be squared. This is only for a Bohr atom, so an atom that has one electron like hydrogen. Z, number of protons, atomic number, N, number of neutrons, mass number is Z plus N. Now, all of these are the types of decay. So we have alpha decay, beta minus, beta plus, electron capture, and gamma decay. We can go through a video talking about this more, but this is just the overview of the net products in just the reaction in general. So alpha decay, we eject an alpha particle, which is said here. And so that means you lose 2 protons, and you lose 2 neutrons, and so that means overall your atomic number is going to decrease by 4. So the easiest way to tell that something is an alpha decay is if the proton number goes down by 2, which makes it a completely new atom. Now, beta minus and beta plus decay, I remember these because beta minus, you're turning something into an electron, so an E minus. Beta plus, you're turning something into a positron, so E plus. So if you just remember those things, you can kind of figure out the pathway of what's actually happened. So beta minus, we know that we're forming an electron. We know that we're forming a negative. And so how are we going to form a negative? We're going to take a neutron and turn it into a proton plus an electron. So neutron, no charge. We're turning it into a proton plus and a minus E, which is also adds up to be no charge. Beta plus, we know that we're forming a positron. So how we get a positron is we change a proton and we turn it into a neutron plus a positron. So we have a plus charge and then a 0 and a plus, which is also a plus charge. So we can also see here the changes in Z, N, and the atomic number for all of these. Electron capture and beta plus are very similar because they both result in the same thing. They both result in a decrease in the proton number by 1 and an increase in the neutron number by 1. But it is not forming a positron, so the mechanism is different. So the result is the same, but the mechanism is different for electron capture. Gamma decay, just emits a gamma particle, so it doesn't change the atomic number or the neutron number or the mass number at all. Kind of confusing a lot, just something you need to memorize, these different kinds of decays. Moving on. Bonding, formal charge, you don't need to remember this equation if you know just how to find formal charges based off of like a drawing or something. Intermolecular force strength, ion dipole, H bonds, dipole induced dipole, stuff like that. London dispersion forces are obviously going to be the weakest. Periodic table trends. So the trends that are going to increase up into the right of the periodic table are going to be electron affinity, ionization energy, and electronegativity. Those are all going to increase going up this way. This is easiest to remember because if you think of like fluorine, it's going to have like the highest of all of these. Now, atomic radius is going to increase as you go down as they're getting bigger, and we can think about that as the opposite of electronegativity. If the protons are not holding on to the electrons as tightly, the atomic radius is going to be greater and the electronegativity is going to be lower. So it is the opposite of electronegativity. Acids and bases, again, they're opposite of one another. Acids increase this way and base strength increases this way. Electronegativity, this is just helpful to know. Again, you can always just look at the periodic table. Okay, all the way back up here, thermodynamics, changing Celsius to Kelvin, you just add 273 to Celsius to get to Kelvin. 1 cal is 4.2 joules. Heat, Q equals MC change in T, and then Q equals N delta H. These are for phase changes, where change in H is the change in enthalpy, which is heat, and then negative change in enthalpy is exothermic because we're giving off heat, positive change is endothermic because we're taking in heat. Standard state, heat of the reaction is always going to be the sum of the products minus sum of the reactants. And just remember here that we need to multiply those H of F values by the number of moles that there are. The different laws of thermodynamics. Energy in the universe is constant, so the change in energy is going to have to be the heat minus the work. All reactions tend to go towards an increased state of entropy. Entropy for a pure crystal at 0 degrees Kelvin is going to be 0, so that's absolute 0. Gibbs free energy, change in G equals change in H minus T delta S. Remember, G is our Gibbs free energy, and that is going to be a determination of spontaneity. G is also negative RT natural log of K. Now moving on to gases, standard temperature and pressure. This is talking about Boyle's law, Charles' law, just talking about the differences in the relationships between these values. But if you know the ideal gas law, PV equals nRT, then you can derive all of this yourself. You don't need to memorize all of these. This van der Waals equation, not extremely important. Just know that it's there. Maybe think about the relationships a little bit. They'll normally give you an equation this complex, but know that it is a thing. Partial pressure, sum of the individual partial pressures are going to be equal to the total pressure. Now, Graham's law of effusion, this relationship is important to know because it's easy to get confused. So if we think about R2 over R1, so the rate of effusion of gas 1 over the rate of effusion of gas 2 is equal to the square root of the opposite. So they're not proportionally related, if that makes sense. So we have 2 over 1 is equal to the square root of 1 over 2. And this side is mass, and this side is going to be effusion rate. And effusion rate is just those molecules like escaping a hole or something like that. Okay, kinetics. The concentration rate, negative change in reaction over time. Reaction rate, you have a coefficient before all of that. The rate law for rate determining step, it's equal to the equilibrium constant K times the concentration of the reactant raised to the coefficient. Arrhenius equation, also knowing that relationship. Okay, all the way up here, equilibrium. We just talked about that equilibrium constant. This is how you find it. Remember, we're only doing aqueous things in here. In gases, we are excluding solids and liquids in this equilibrium constant equation. The relationships between KEQ and 1, if KEQ is greater than 1, products are going to be favored, and we can think about that is if KEQ is products over reactants and there are more products, the value is going to be greater than 1, so it's going to favor the products. Now, reaction quotient is the exact same thing, it's just not taken at equilibrium. So this can help you determine where the reaction is going to proceed in order to get equilibrium. So Q is less than K, then it's going to need to react in the forward direction because we're going to need to make more products to increase that value of Q to eventually get it to K. Acids and bases, pH equals negative log concentration of H, same thing for OH, pH plus OH equals 14. All of these good equations are very important to know. They multiply to equal 10 to the negative 14. How to find Ka and Kb. It's the same as the equilibrium constant equation, except for it's just dissociation. So it's HA goes to H plus A minus, but it's still products over reactants. pKa, Ka, same thing. Henderson-Hasselbalch equations. This is very important. I would just pick one of these to remember and not all of them. And then from these we can use our other identities to get to whatever the question is asking for. So I usually remember the one that is highlighted, which is pH equals pKa minus log HA over A minus. So just Try not to get it confused because a lot of people switch the positive and the negative, which switches the relationship between the log. It doesn't matter which one you memorize, it'll get you to the same answer either way. I've just tried to memorize one and not confuse yourself. Acid-base neutralization. This is for like titrations and stuff. Again, you don't really need to memorize this equation if you understand how like titrations work. Okay, last section. This is redox in electrochemistry. So this first part is determining the oxidation state, or OS. So pure elements are going to be 0. Neutral molecule is always going to be 0. And then the sum of the oxidation state is always going to be the charge that is on the ion. So like for group 1 metals, we have +1, group 2, we have +2. For F, we have -1, H is +2, O is -2. These are common ones that are just helpful to know. Faraday's law of electrolysis, basically saying that the amount of chemical charge is proportional to the amount of electricity that flows through the cells. So this is kind of the basis of our electrochemical cells. If E cell is positive, it's going to be spontaneous. If it is negative, then the opposite reaction is going to be spontaneous. So if we have like a galvanic cell or something and we want to make a spontaneous reaction, we need to make sure that E cell is always going to be positive. And this is tricky because if you remember Gibbs free energy is negative if we want it to be spontaneous, but this is different. And then the Nernst equation. That was a whole lot of information that I just threw at you. But this is the overall formula map of everything Gen Chem, all the like important concepts I'd say. There's obviously more little things that you'll get through practice, but I think this is a good thing just to go back to if you ever forget. Like if you ever forget the different types of decays, you have that right here. If you want a more in-depth talk about any of these topics, let me know. This entire formula map will be on my link tree and it will be under general chemistry notes and then formula map. But that is all I have for this video.